In the DC circuit, the power is defined as the product between voltage and current. However, in AC circuit, the voltage and the current, there could be a phase shift. So we have to take into account of this case. Here there are three simple circuits. The first one, it has only a resistor. And if we consider the AC voltage applied to the resistor, the green represents the flow of the current. The voltage across the resistor is also in phase of the current across the resistor. So this is how I will draw it. The AC power is defined as the product of the AC voltage and AC current. In the case of a simple resistor, the power is non-zero or positive, and this is the FH power actually consumed or converted into heat or work in the load. And in the phasor, we'll put the current along here. And the voltage also in phase, so we put the voltage along here as well. And in general, the wheel power P is defined as the root mean square value of the voltage times the root mean square value of the current and times the cosine phi. Phi is the angle between the voltage and the current. In this particular case, phi equal to 0. So this is the wheel power P. Next, let's look at another circuit. In this circuit, we have only a capacitor, and the current is represented by the green. The AC current is represented by the green. Now, if you imagine you measure the voltage across the capacitor and compare the current flowing through the capacitor, and you will find there's a phase shift between the voltage and the current, and the voltage is 90-degree lag of the current. So in the phasor, this is how we'll draw it. This is the current here, and the voltage is 90-degree lag from the current. So I will put the voltage here. And the angle between this one is 90 degree. In the time domain, this is how I will draw it. So the angle between the current and the voltage is 90 degree, and this is the phi. This time, now remember, the AC power still defined as the AC voltage times the AC current at each moment of the time. If you perform the multiplication, and if you notice how this graph shifts relative to each other, you will find the FH power is equal to 0. So the FH power across the capacitor is equal to 0. Now we can look at the curve. Now within this period here, from here to here, both the voltage and the current, they are positive. So the power on the capacitor is positive. From here to here, the voltage is positive, but the current is negative. So there's a negative power on the capacitor, it means the capacitor is releasing its energy back to the circuit. And if you go through the mathematics, you will see those power stored in the capacitor is the same as the power released back. So the overall is 0. And you can analyze the curve similar. So what I mean is there's a period of storing energy and a period of releasing energy. Now we can look at a couple of more definitions in the phasor here. So we can say P, the real power for the pure with capacitor circuit is VR ms IR ms cosine theta, and in our case theta is 90 degrees, so it is equal to 0. But we can also define another quantity, which is Q. Q is V would mean square, I would mean square, and sine theta. In this particular case, theta equal to 90 degrees, so this is a non-zero. So this Q here, this number mean is the amount of energy stored during this phase, and also equal to the amount of the energy released during this phase. So this is how much energy stored or how much energy released during the storing phase or releasing phase. However, on average, it's still 0. So we call the Q reactive power, the amount of power stored and released by the capacitor. We learned if there's an AC applying to the resistor, we have a real power. This power will absorb into or convert into heat and work done in the load. If you have a capacitor, there's no real power deposit to the capacitor or consumed by the capacitor. The capacitor will store the energy and release the energy. So the average power is 0. Now let's look at this case. If we have a circuit, the resistor and the capacitor, they are connected in series. So according to the Kirchhoff law, the current passing through the resistor and the current passing through the capacitor is equal. Now we can measure the voltage across the resistor, the capacitor, and the power supply. So let's do it the three things. First, what is the voltage across the resistor? We call it VR. This voltage again will be in phase of the current. So I will draw the voltage the same here. Next, if we measure the voltage across the capacitor, here we see, and the theory, the physics also say the voltage across the capacitor will be 90 degree lag behind the current. So this will be the voltage across the capacitor, which is 90 degree. Now note the voltage across the capacitor doesn't have to be equal in the magnitude, but here I just do it as a convenience. So let's review. The green represents the current, and this current is the same passing through the resistor and the capacitor. The oranges represent if you measure the voltage across the resistor, it is in phase. Now if you measure the voltage across the capacitor, and you will find it shifts 90 degrees behind the current. So how we represent this one in the phasor diagram? So let's do it. This is the current, and this is the voltage across the resistor. And here it is the voltage across the capacitor. So the question is, now what is the voltage of the power supply? So in this case, you have to do the vector addition. So you add the two voltage, but this time they are vector. So if you perform the vector addition, that's what you will find. So this, the wet one, is the voltage here. So what I mean is, now if you measure, you put another voltmeter here. If you measure, this is the apply or the source voltage. And you will find this voltage shift in between the voltage across R and the voltage across the capacitor. So in terms of the drawing here in the time domain, and this is what you will find. And this is in between. Now you can see that's why engineers prefer to represent all this in a phasor. So phasor is very clear. Now what's next? Next is, of course, the angle. Now remember, this now is the input voltage, the RMS value. And the green one represents the I of the input as well. And this is the angle phi. RMS, IRMS, it is another power. We call it apparent power, and we call this one S. Now we can represent the apparent power S along the mean square value of the applied voltage. So I will put S here. So now we can project the S along the phase of the current, and this is here. And we call this wheel power. And the angle here is phi. And now if we project the apparent power along the voltage across the capacitor, this is Q, this is reactive power. So we can form a triangle, and this is the very useful triangle. This is S, P, and Q, and this is phi. And of course Q equal to S psi phi, P equal to S cosine phi. So the P represents the wheel power consumed by the load, and the Q represents the reactive power put in and out to the capacitor in our case. Okay, let's see how we should answer this question. The first one, definition. A, what's the wheel power? So the wheel power, P, in mathematics is defined as the root mean square value of the voltage times the root mean square value of the current, and cosine theta. And remember, because this is the real power, the power really consumed by the load, so we use watt, it means joule per second. In watt, it means the average power actually consumed or converted to heat or the work in the load. Second, what is the reactive power? reactive power, we use Q denote reactive power, and it would mean square value current psi theta. So just recall so this is the wheel and this is reactive, and this is the angle phi. So the reactive power is the power which alternatingly, so it is stored and released. Each alternated, stored and released each cycle by capacitor or inductor. Last is the apparent power S. So the apparent power S is just defined mathematically as the root mean square value of the voltage times root mean square value of the current. And incidentally, I just have to remind you, now reactive power is a power, so it is joule per second, but engineering try to remind you this is a reactive power, is the power will store and release in a cycle. So therefore, instead of writing W, a joule per second, is VAR. You can treat VAR as joule per second, but just like a reminder, it reminds you the nature of this reactive power. Okay, apparent power, that's again, in terms of the power, the unit is joule per second, but this time we're going to use VA to represent, and this is just the product of root mean square voltage and root mean square current. Okay, so it is the total power the supply must deliver. Okay, it is the total power the supply must deliver. B is what is the power triangle. Now power triangle, again, it depends on how you draw the triangle, and now for the power triangle, we always draw the baseline as the real power, the power delivered to the resistor, and the vertical line represent any reactive element. Say it can be a capacitor, it can be an inductor, or the combine of capacitor and inductor. And we put a Q here. And now the hypotenuse is here, S. So put it a bit better. This is PQS. And this is the angle phi. So Pythagorean theory say S squared equal to P squared plus Q squared. And the power factor is defined as the cosine theta, and of course it's equal to P over S. This question is about a motor in a workshop. The wheel motor consists of a set of coils. This coil will behave like an inductor, and also because this is a coil, so the coil it carries resistivity or resistance. So we can model a wheel motor by a resistor in parallel to the inductor, because the resistor and the inductor, they are connected in parallel, so they have the same voltage. It means same magnitude and the same phase. So the oranges represent the voltage V, and the current is also along here. In the past, the inductor and the resistor, they're connected in series, so they have the common current, but this time they will have the common voltage. And we know from the basic theory, the voltage of an inductor is 90 degrees ahead of the current. However, this time we have to align the voltage of the inductor to the voltage of the resistor. So we have to rotate the phasor of the inductor by 90 degrees. So the oranges here also represent the voltage across the inductor. It means now they have the same magnitude and the same phase. Since we rotate the voltage, the current has to rotate as well. So the current this time will be here. Now, this phase relationship is still exactly the same. It means the voltage is 90 degrees ahead of the current. So there's no change in the physics. So now we can combine both diagrams. This is the common voltage here, and this is the current passing through the resistor. And this is the current passing through the inductor. This one is where the current flowing out from the supply. Now this time we can use the current as the reference of the different type of power. The real power, which is the power converted into the heat or the work done of the motor, and this is P here. And this is equal to V. Remember, V is common for all the elements, and multiply the current passing through the R. This time the apparent power S will along the current. So it will along here, and this is S, and this is the angle phi. The reactive power is come from the inductor. So this is where the reactive power here, Q. Now the apparent power is equal to the voltage multiply the root mean square value, both root mean square of course, of the total current. It means the current, this part. The power triangle can be drawn as this. Now the question say it has a power factor 0.7. So the definition of power factor is PF equal to cosine phi. So phi is equal to inverse of 0.7, and you will find this is equal to 45.6 degrees. So this is 45.6 degrees. And the real power P, of course, is equal to apparent power times cosine 45.6 degrees. The apparent power is 10 K Now remember, this is apparent, so we use VA as the unit times 0.7 because this is the power factor PF. The apparent power is 10 kVA. Remember, VA is the unit, so we just put 10 K here. The power factor PF is cosine 45.6, so this is 0.7, this is times. So this is 7.0 K watt. Watt, we use the watt because this is the real power. Now the reactive power, it means the Q. Q here is where the power stored and released by the reactor. And Q here is the power stored and released by the inductor. So this is S sine 45.6 degree, and this is 10K sine 45.6 degree, and you should get 7.14 K. Now this time, because this is a reactive power, even though this is joule per second, but the convention is using VAR. So you can see this is not desirable because the real power is only about 70% of the apparent power. So what people usually do is they will connect the motor in series with a capacitor, and we call this one shunt capacitor. When we connect the capacitor in parallel to the circuit, that is how we will look like. We have here, and then we have another capacitor C. So what happens is, after you connect the capacitor here, the voltage across the capacitor remains the same as the voltage across the R and L. But this time, remember, for the capacitor, the voltage is 90 degrees lag behind the current. So if we align the voltage of the capacitor to the R and L, the current of the capacitor must be joined like this, IC. Just incidental, this is IL. So this one here, you can say after we put the capacitor in parallel, here, this is IC. So you have another factor, which is the power on the capacitor. So we have a two reactive power, but they are out of phase. So I should put this one here. Now it say I want to put a capacitor such that the new overall Q is equal to 0.95. So what I mean is, after you add these two together, you want this one become 0.95. And this is how I will draw Q, the new value of Q after you put the capacitor. And now you have this one here, and this is the new angle. The new power factor is 0.95, and so the new angle is at inverse of 0.95 and it is equal to 18.2 degrees. Remember, the P remains unchanged, which is 7.0 K watt. So we can use this one and say tangent 18.2 degree equal to Q over P. And the new Q is equal to P tangent 18.2 degree, and this is 7.0 K tangent 18.2 degree, and you will find this equal to 2.3 K VAR. Now can you see, before we add the capacitor, the Q is equal to 7.14. Now after we add the capacitor, the overall Q is 2.3 K. So what I mean is there's a reactive power contributed by the capacitor. So this reactive power QC, if we look at here, the QC must equal to 7.14 K minus 2.3 K, and this is equal to 4.84 K VAR. Next, let's check about how we calculate the QC. Now, of course, QC, the reactive power is equal to VC multiplied IC. Next, we ask the relations between V and I. We have a Ohm's law for capacitor. So this say the V across the capacitor is proportional to I across the capacitor, and the proportional constant is XC, just like the Ohm's law. For the capacitor, XC is equal to 1 over omega C. So we plug this one back. From here we know that IC is equal to VC over XC, and it means equal to VC omega C. Plug this one back, and QC is equal to VC, and this one is VC omega C. Therefore, we have a relationship here. This is for part C. The part C say what value of capacitor you should include or you should put to reduce the overall phase angle or the power factor. So we can find this value by QC equal to V square omega C. So C is equal to QC, the reactive power, over V square omega. Reactive power we just calculate is equal to 4.8. So this is 4.84 K, and the voltage is the total voltage. So this is 240. They're all the same. Multiply omega 2 pi f. 2 pi f is 50 Hertz, and you will find this is 268 mu f. In this question, it say an oscilloscope measure the current lag the voltage by 53 degrees. Now there's a lot of combination, but let's make it simple. We assume this is a parallel circuit like the one we studied last time. This is the voltage V, and the current lag behind. So this is the current I here, and the angle here is 53 degrees. Let's put down the value here. So I is 3A. Now we assume all the value they are in RMS, and the V is equal to 100 V. And now we find what is the apparent power. apparent power S is equal to VI, so it's equal to 100 times 3 and equal to 300 VA. So now we can draw the power, the apparent power along the I. So this is apparent power S, and the angle here is 53 degrees. The real power P is apparent power cosine theta. So it is 300 cosine 53 degree, and you will find this equal to 180. Remember, this is the real power, so we use watt. The reactive power Q is equal to S sine phi, or phase angle, and this is 300 sine 53 degree. And you will get this is 240, and the unit is VA, reactive. This is R. So how we draw the triangle? The S project along here, and this is the real power P, and this is reactive power Q. Now part B, it explains what part of the current contribute to heating. So the current is here. So it is the current along the V contribute to the heating. So this is the I cosine 53 degree is really the current passing through the load, and we'll say this is 3 times cosine 53 degree is equal to 1.8 ampere. We assume this circuit is about a motor. We can model the real motor as a parallel of resistor and an inductor. So I can draw the voltage along here. This is the common voltage. And the current passing through R in phase, of course, and the current passing through the inductor here is 90 degree lag, and this is the current of the power supply. So this is I power supply, and this is IR, and this is IL. Now this is exactly the apparent power, and when the apparent power projects to the resistor, this is the real power P, and this one here is the reactive power Q. The real power P equals to 1000 volts. From the power triangle, we can say tangent phi equal to Q over P. Therefore, the reactive power Q is equal to P tangent phi, and Q is equal to 1000 tangent. Now the phi is the inverse of power factor. So this is here, and you can see the phi is equal to 45.6 degrees. So this is 45.6 degrees. And you will get this is equal to 1020 VAR. So after you put the capacitor in parallel to the circuit, the P remains unchanged, but the Q will reduce. So the Q will reduce to a lot more smaller. This is your Q2, and this is your new apparent power. And of course the angle here also reduced, so the cosine angle will increase. So this is equal to 0.95. So you can see phi 2, the new angle will become 18.2 degrees. Now again we can use trigonometry and find tangent the new angle equal to Q2P. So Q2 equal to 1000, and this is tangent 18.2 degree, and you will find this become 32A VAR. So why is reduced? Because now you can see here, originally we have a Q here. This is Q1, and this is equal to 1020. Now because you put a capacitor, so the capacitor have another Q. This is QC, and the sum of these two is equal to here. So this is your Q2. So the QC will reduce the reactive power, and you can see from here the Q1 or the QC should equal to Q1 minus Q2, and this is equal to 1020 minus 328 and equal to 692 VAR. This is C. Part D. So just recall, QC is the voltage V multiply the I passing through C, and the voltage and an I V is proportional to IC with a proportional constant XC, the Ohm's law for capacitor, and V is equal to 1 over omega C IC. So IC is V omega C. So we can say the reactive power C is V squared omega. C is the capacitance, so C is equal to QC V squared omega. So QC we just found is 692, and the V is the voltage, and the voltage is 240. So 240 squared 2 pi 50, and you should be able to get the value is equal to 38.3 roughly mu F. Since the question is actually asked for the capacitor's reactance XC, so we can start from here. Again, QC is equal to VIC. Now in a way everything can be like a parallel, because P is equal to VI. Of course this is I cross the R. This is the wheel power. Now for the Ohm's law, which equal to V equal to IR, so therefore we can say I equal to V over R. And now if we substitute this one back to here, for the resistor, P is equal to V R, it means V squared over R. And the same happened for the reactive power. So V here, the Ohm's law for the capacitor equal to XC I. So the I, this I is the current passing through the capacitor. IC equal to V over XC. So now we substitute this I back to here. And we can say the QC is equal to V over XC, and similar is V squared over XC. So this is a very similar to the case in capacitor. So XC is equal to V squared over QC, and our V is 240 squared. QC is 692. So you can find this roughly equal to 83.2 ohm. Because the voltage phasor is at a 0 degree, so I will put the voltage here, V. And it say the current lag by 30 degrees. So I will put the current here, I, and the angle in between is 30 degrees. Now this is the phasor between the voltage and the current. How about the power? So the wheel power will along here, and the apparent power will along here. This is S, and this will be 30 degrees. And from here we can say this is the Q. So by definition, apparent power S is equal to root mean square value V multiplied root mean square I. So it is 150 times 4, and it is equal to 600 VA. The wheel power P is S cosine 30 degrees. So it's 600 cosine 30 degrees, and it is equal to 520. The unit is W, watt. Reactive power is equal to S sine 30 degrees, so it's 600 sine 30 degrees, and equal to 300 VA reactive R. The power factor PF is equal to cosine 30 degrees. So it is equal to 0.866, and it is lag behind. Now from this diagram and from what we learned before, it's very clear this phasor or this power diagram is represent the load is a inductive. So this is a typical characteristic. Say for example a motor, and so you will model the motor as a inductor in parallel with a resistor, R and L, and this is the source. In this case, they have the common voltage, so that's why we put the voltage here alongside the common, and the current is here. Okay, and this I current is the current passing through here. But remember, the current through the L and the R will be different. This is IR, this is IL. And if you look at the phasor here, this will be your IR, and this is your IL. In terms of the power, this is how the power triangle will look like. Again, this question is about an inductor motor. The real inductor motor can be modeled as a parallel resistor and an inductor. And the power triangle is look like this. The real power is equal to apparent power cosine phi. The power factor PF is equal to cosine phi and is equal to 0.72. And from here we can say phi is equal to inverse 0.7 and is equal to 44.0 degree. So S1 is equal to P over cosine phi, or it is equal to 2.0 K over 0.72. So S1 is equal to 2.78 K, and the unit is VA. Q1 is S1 sine phi, so it's equal to 2.78 K times sine 44 degree, and it is equal to 1.93 K VAR. And the question say it want to improve the power factor from 0.72 to 0.95. So what it means is reduce the angle. So let's look at it. We want the cosine phi 2, the new power factor, equal to 0.95. So it equal to 18.2 degree. Also, from the power triangle, we can say tangent phi 2 equal to Q2 over P. So Q2 equal to P tangent phi 2. So Q2 equal to 2.0 kV or 2.0 K times tangent. The new angle, it is equal to 657 VAR D. Now let's analyze the relationship between Q1, Q2, and QC. The reactive power is due to the inductor, so we call it Q1, and by putting a capacitor Q1, and the capacitor is opposite here, QC, and the sum of this one is what we find Q2. So it is very clear that QC is magnitude is equal to Q1 minus Q2, and Q1 is equal to 1930 minus 657, and is equal to 1273 VAR. E, the power formula, QC is equal to VIC or V squared over XC, are similar in analogy to P equal to VI for the resistor, and I square R or V square over R. The 3 here, and in our case R is equivalent to XC. Okay, so XC is equal to V square over QC. So this is equal to 240 square, and this QC is the one we just found, is 1273, and we found this is 45.2 ohm. F, because we know XC is equal to 1 over omega C, the C is the capacitance, so C equal to 1 over XC omega, so 1 over 45.2 to pi 50, 17.3 mu F.